So far, we've discussed that neural networks are able to solve or approximate any given function, and a single hidden network can do that, and deeper networks can do that more efficiently. But I'm going to draw your attention to the most important problem in the universe. Where's Waldo? And if we are able to solve this problem, we can do a whole lot more, right? We can find cancer cells, for example, and go from there. So the problem of finding Waldo in a given image, if you think about it, is really flexible. Since neural networks are universal approximators, can we design a neural network that allows us to find Waldo? That's what we're going to do. Moving on, so this is what Waldo looks like, and I welcome you to spend some time in trying to find where he is, or whether he is in this image or not, which can be modeled as a classification problem by itself, like whether Waldo is in the image or not. Just like we can label a given cancer image, an image as cancerous if it has tumor cells in it, right? So it's pretty much the same problem over here. So I'm going to use a simpler, or what I call this social distancing edition. I found these on the internet. Good job to their creators. And this is a really simple puzzle, right? We can see where Waldo is. But let's say we want to localize where he is, and we want to solve this problem using neural networks. So we are given a bunch of training data in which we know where Waldo is, and we are going to use that to approximate in a given picture where he is in that image, or whether he is present in that image or not. That's what we are going to do. We feed an image as input, and then at the output of the image, we get a location or a box around where Waldo is. You can think of different variants of this problem. Let's say if you want to model it as a classification problem, you take the image as input and you spit out a number, or the neural network spits out a number saying that whether Waldo is present in that image or not. But this is what is called an object detection and localization problem. And what we're trying to do is that we're trying to localize where Waldo is by putting a box around them. So the output of the neural network should be this thing. So an input of the network is going to be an image, and the output of the network is also going to be an image. And since neural networks are universal approximators, we should be able to solve this problem, right, using machine learning. We just need some training data, right? And if we think about how we can solve this, let's say the input image size, if it is 256 by 256 by 3, 3 being the RGB channels, and if you flatten it, then we end up with about 196608. That's the dimensionality of your input. And then you have the same dimensionality of your output, except that in the output we need a box around where Waldo. To use a single hidden network for this, we are going to need a very large number of parameter values. The number of weights that we are going to need is large. And just like any estimation problem in which you are trying to estimate an unknown quantity, in this case we're trying to estimate the weights of the network, the number of weights that are to be approximated, if that is pretty large, we are going to need even a larger amount of training data for that. That is one of the fundamental paradoxes of learning, right? To approximate, we need input data. And the more weights we have, the larger data set we're going to need. So that is going to be a problem, not only just for optimization, but also in terms of the requirements on the training data. We're going to need a very large number of sets to be appropriately able to generalize to unseen cases. We can use a deeper network, and that's going to reduce the number of required parameters, but still a very large number of parameters are going to be needed. How can we solve this problem? This type of problems was a solution to this problem was proposed by some excellent researchers in machine learning, and they came up with a very cool idea that instead of having a network that is fully connected, so when we have a network like a multi-layer perceptron, we have a network like this one, right? So we have all of these inputs, input dimensions, and they're going to be like, there are going to be 196608 dimensional as input, and then we have some neurons that are connected over here, and each of the inputs is connected to this neuron, and this goes on for each of those neurons. So let's say if we have p neurons in this layer, then the number of weights that we are going to get is a product of these two, right? And then these are going to feed into the next layer, and then we have each neuron is going to be connected to each other network in the neuron in the next layer. So this is what we call a fully connected or a dense network, okay? Or we can call it a dense network. Now, because the number of required parameters in this is very large, One way that people thought that we may be able to do better was that instead of having a fully connected network or a multi-layer perceptron that is fully connected, we can have a different architecture of the neural network. And that type of architecture is called a convolutional neural network. And that's what we're going to discuss next. It reduces the number of parameters that you need for this particular task and for other tasks. And it gives you, so that reduces the optimization burden, the computational complexity, but also reduces the requirement on the number of training examples. And the way it does it is by having a sort of a hierarchy, and we're going to see what that means in just a bit, built into the network, and sharing weights across different regions in the network. If you look at this particular network, each pixel in your image is going to become a single input. And each network, each neuron over here is going to have its own set of weights that is going to multiply that pixel value with, right? In a convolutional network, we can have different type of, as we call them, filters. Those are going to be shared, and they're gonna, so a number of pixels goes into, a bunch of pixels goes into a filter, and they get multiplied or something happens to them, and the next bit of pixels also go into the same filter. So the filter is actually the weights of the neural network, and because those are shared across pixels, you end up with fewer number of parameters. We're going to revisit this important concept once we have talked about what convolution is and how it leads us to building these interesting convolution neural networks. Remember, we are trying to find Waldo. So let's have